All right, welcome everyone. If you're new to the Plastic Processing Engineering Technology program, you are in exactly the right place. Today, we're going to dive deep into a really cool and versatile process called rotational molding. This is how we make all sorts of massive hollow plastic parts. So just look at this stuff. Kayaks, giant industrial tanks, those super tough coolers that you see everywhere. I mean, at first glance, you might think, wow, how do they even make something that big and complicated in one single piece? Well, believe it or not, they're all made using this really elegant low-pressure method. So what's the secret? Okay, so here's how we're going to tackle this today. First up, we'll cover the basics. What exactly is rotational molding? Then we'll walk through the 4 main steps of the process itself. After that, we'll get into the nitty-gritty of materials and the molds you'll be using. And to wrap it all up, we'll talk about troubleshooting some common product defects. Sound good? Let's jump in. So what's the big idea here? Honestly, the easiest way to picture it is to think about making one of those hollow chocolate Easter eggs, right? You have a mold, you put your material inside, and then you just swirl it around with heat until the entire inside surface is coated. It's pretty much that simple. The really key thing to remember is that this is all done with very low pressure, which, as we're about to see, is a huge advantage. But how do you get that perfectly even coating inside the mold? Well, that is the magic trick, and it's called biaxial motion. Biaxial just means it's spinning on 2 different axes at the exact same time, kind of like the Earth spinning on its axis while it's also revolving around the sun. It's this complex tumbling motion that forces the melted plastic powder to get into every single nook and cranny, building up these beautiful uniform layers. Now, as a future technician, this is super important. You need to know why you would pick this process. And since it's low pressure, the molds don't have to be these massive, expensive fortresses of steel. That makes the tooling way, way cheaper, especially for large parts. Plus, you get these incredibly durable, stress-free parts with even walls, which means they're much less likely to crack. It's a real win-win. Okay, so we've got the principle down. Now let's walk through the actual manufacturing cycle. You'll see it's a pretty logical 4-step dance that takes you from raw powder to a finished product. This visual breaks it down perfectly. Step 1, loading. You just put a precise amount of plastic powder into the mold. Step 2, heating. You close it up, send it into a giant oven, and start that biaxial rotation we talked about. The powder melts and coats the inside walls. Step 3, cooling. The mold comes out of the oven, but it keeps spinning. That's key. And it's cooled with air or a water mist to solidify the plastic. And finally, the best part, step 4, demolding. You pop open the mold, and out comes your brand new one-piece part. Pretty neat, huh? But, you know, a great process is nothing without the right material. The plastic you choose is what gives the final product its personality. Is it going to be flexible, super rigid, able to handle extreme heat? It all comes down to the material. And when it comes to materials in the rotomolding world, there is one that absolutely dominates. I mean, look at that. Polyethylene, or PE for short, is the undisputed king of the castle, making up a whopping 85% of all materials used. And it's no surprise. It's tough, it's forgiving to process, and it's cost-effective. It's the ultimate go-to material. But polyethylene is really a family name. You're mostly going to encounter 2 types, LLDP and HDP. Think of LLDP. That's linear low density, as the tough but flexible one. It's got amazing impact resistance, which is why it's perfect for a kayak that's going to bang into some rocks. Then you have HDP, high density, which is the strong, rigid type. You'd use it for things that absolutely need to hold their shape, like a boat dock or a large industrial vessel. But here's where things get really exciting. PE is the workhorse, for sure. But check this out. Advanced materials are completely changing the game. This chart compares the stiffness of PE to polyamide, which you probably know as nylon. It's literally 4 times stiffer. What does that mean? It means you can design parts that are way thinner and lighter, but just as strong, and they can handle more heat. This is a massive deal for industries like automotive, where every gram counts. Okay, we've talked process, we've talked material, but what actually gives the part its final shape and texture? The mold, of course. The mold is everything. Its surface becomes the part's surface. Its shape becomes the part's shape. So let's dive into the world of tooling. And you've basically got 2 main choices here, and your choice has a huge impact on the final product. On one hand, you have beautiful CNC machined aluminum molds. They transfer heat like a dream. which gives you that amazing high-gloss finish you see on a premium cooler. But they're expensive. On the other hand, you have welded steel plate molds. They're cheaper, easier to modify, and perfect for big, simple things like an agricultural tank, where a perfect surface finish just isn't the priority. In this picture really says it all. This is a mold for a high-performance automotive air duct. Look at those curves, that complexity. There's just no way you could get that kind of precise geometry with a simple welded steel mold. This is where CNC machined aluminum truly shines and opens up a whole new world of design freedom. Now, for your diploma, you definitely need to know a mold's basic anatomy. You've got the parting line. That's just where the two halves meet. You have clamps to hold it all together. But I really want you to pay special attention to the venting system. This little tube is absolutely crucial. See, when you heat the mold, the air inside expands. If that hot air has nowhere to go, it's going to cause all sorts of problems, like ugly bubbles or a warped part. That tiny vent prevents all of that. All right, let's switch gears and talk about troubleshooting, because, let's be real, things don't always go perfectly on the factory floor. A huge part of your job as a technician will be playing detective, identifying what went wrong and knowing how to fix it. So, what are the common problems you're going to encounter? Even with a process as robust as this one, you're going to run into a few common headaches. These are the big four you'll see time and time again. Incomplete filling? You probably didn't put enough powder in the mold. Warping? Your cooling was likely uneven. Bubbles? Check that vent we talked about. It's probably blocked. And if you see a burnt charred spot, well, you either cooked it too hot or for too long. Each problem gives you a clue, and it almost always points back to your process, your material, or your mold design. And here's a pro tip. Probably the most important one for preventing defects. Think ahead. Good design is your best friend. Look, plastic powder does not like sharp internal corners. It has a tough time flowing into them. But simply designing with nice, generous, rounded corners instead, you make it so much easier for the material to flow evenly. It's a tiny design choice that makes a massive difference in the part's final strength. So let's end with this thought from Professor Roy Crawford, a true pioneer in this field. He basically said that the full potential of this process is locked behind the materials we have available. We already saw how materials like polyamide are starting to change the game, but that leaves a question for you. As the next generation of technicians and engineers, with new materials being developed all the time, what new products will you help create with this incredibly versatile process?